your ds vector for that little surface is exactly dx, my bad, I'll get it eventually here, dx dy z hat, right? That's your, if you want to look at this as a surface in 3 dimensions, you could do that, right? R as a surface in 3 dimensions is a rather silly type, but my point to you is the boundary of R, right? Defined by the right-hand rule, by the way. What's the right-hand rule? This is yet another way of looking at orientation, all right? So the right-hand rule says this. You take your right hand and you point your thumb in the direction of the normal, all right? Then your fingers will curl in the direction. They will wrap around the boundary of the surface in the direction it should go. See that? See it? That's another way of saying that rule I told you guys the other day, which is if a little dude walks along the top of the surface should stay on his left if he's walking in the positively oriented direction of the boundary. All right? So, with respect to this setup, we have already proved, right? We've already proved the theorem that pdx plus qdy is equal to the double integral over r of partial q partial x minus partial p partial y dA, right? But my point to you is that that is actually equal to the line integral of the 3-dimensional vector field pq0 dot dr, right? And the surface integral, if you like, s, let's say, and I guess I could say boundary of s over here, of the curl of f dotted with ds. It's just that my ds is dx dy, and the surface that I'm talking about here is just this. I mean, this is the surface. It's just a subset of the xy plane. Are we all in agreement, like, that we can look at Green's theorem as a line integral and a surface integral of a very special type, right? So let me just try to expand your mind for a second. If we can do this for the xy coordinate system, right? You can take an arbitrary surface, right? And you can invent xy coordinates. See, that's a weird idea, isn't it? My point to you is if I have a surface that's some kind of wackadoodle, you know, whatever curved surface, and I've got, you know, let's say x bar, y bar, z bar coordinates. If I take a point here, I can build a coordinate system. I can build a coordinate system like this that's got z this way, that's got y that way, and that's got x that way. So that basically on this little patch on the coordinate system, I can invent x, y, z coordinates. And I can apply the Green's theorem we already know to calculate the integral. I can basically apply Green's theorem in a little patch close to z, close to the point I'm picturing, because there it would be true. Like if the surface happens to be flat, right, like this one, if it happens to be flat, I can literally apply Green's theorem to like an xyz coordinate system based on that little patch. So what I said is that if you think about this, I can adapt the Green's theorem to say, well, what I really have is that if I have, you know, like a little planar region with coordinates u and v, then the integral around the boundary of a little planar, closed polygonal region like this, over the boundary of that will be equal to the integral of the curl over the surface, the component of the curl, which is in the normal direction to the surface du dv. Which is to say that what I'm really trying to say is I can meaningfully apply Green's theorem to an arbitrary planar region. So what happens then? If I can apply Green's theorem to a polyhedron like this, to each one of these regions, what happens when you add together Green's theorem on each one of the polygons? What's that? I didn't hear you, I'm sorry. I integrate, yeah. Well, yeah, I'm supposing that, like, what I'm trying to say is what happens if you calculate calculate the flux of the curl of a vector field across this kind of polygonal region. Well, what we understand that would be is the integral of the flux of the curl through each one of the subpolygons, right? And then you add them together. That's just the definition of integration. But for each one of those regions, I can apply Green's theorem. So I would then get the sum of the integrals, sum of the integral around the edge of each one of these regions. What's the boundary of each polygonal region, though? Like this one, it's oriented that way, right? This one's also oriented that way. It has to be oriented that way so that the normal is out. So I'm supposing that the normal vector field to the surface as a total is like this way, all right? So that one. Notice that the edge goes down for this, but it goes up for this. You've got this situation, all of the interior edges, wherever you have two polygons meeting at an interior edge, the interior edges which meet are reversals of one another. So when you add up all of the integrals along the edges, those all cancel out, except for what? Except for this part down here, right? Where it's an exterior edge. So that's why if we think about S as a polyhedron, we get this theorem because we can apply the theorem on each face. When we add the integral up over all the faces, the area integrals just give us the total integral, which is the surface integral. And the line integrals conspire so that all the interior edges cancel. You should have a strong sense of deja vu in what I'm saying, because it's essentially the same argument I used to do what? To prove that Green's theorem, if you could prove it on a little rectangle, you could just as well prove it on a more interesting shape if you took the shape as a union of said rectangles. We had a very similar argument there. So this is just putting equations to the words I just gave you. If I take the sum over all the end faces, I get the sum over the edges is equal to the sum over the integrals, the areas rather. And so this just gives me, on the one hand, the integral of the flux of the curl over the union of all the faces, which is just what we're calling S. And the more interesting thing, of course, is that when we take the integral over the edges, all of the interior edges cancel because the line integral of a curve and its reversal are equal but opposite, they cancel. And so the integral over the sum of the edges just gives us an integral over the boundary of S itself, which is the exterior edge. And I call this baby Stokes theorem because not every surface is polygonal, right? Like the cylinder's not a polygonal surface, right? Like a polygonal surface is a surface that is built from a union of a finite collection of planar regions pasted together. Yeah? Like a cube, for example, or a tetrahedron. But what do you think we could do with this argument? One way we could go is, could you approximate an arbitrary surface with a polygonal approximation? I mean, think about it. If you take more and more and more points, you get a finer and finer, approximation of a curved surface by a polygonal surface, and taking the limit as the number of polygonal sample points goes to infinity, we ought to be able to prove Stokes' theorem in that kind of limit, in the limit of the polygonal approximation going to infinity. So that's one way we could prove Stokes' theorem. Now there are other ways, which I'll show you one of the future classes, but I just wanted to make sure that today we're all here. I want to make sure everybody leaves this class knowing this is divergence theorem, this is Stokes theorem, this is what I need to learn. And like the next homework is pretty much about learning these two theorems, I think. So, yep.
So with that,